And go. I know.
Okay.
I know. We're awake. We're awake.
Okay, so let's go back a couple of lessons. A charge that's moving through an electric field experiences a force according to how intense the electric field is, how much charge you got, how fast it's going, and the angle that the magnetic field is to the velocity. That's what this angle is, the angle between the velocity and the magnetic field. Okay, so that's all good. What if you had a line of charges, all moving at the same speed through a magnetic field? They're all moving through a magnetic field. Well, if they're all going the same speed, if they all got the same charge, and the magnetic field didn't change, they all experience the same force.
Mm-hmm.
And if it's a proton, the velocity is this way, and the magnetic field is in, then that force is going to be down. They're all going to experience a force that's down.
Yeah.
What if the charges were in a wire?
They can't fall. So they have to be so it has to be current.
Well, here we've got protons which can't move.
Yeah.
They're going to experience a force as they move through.
Yeah.
That'll want to make the wire go down. Yes.
Yeah, yeah. That's kind of thinking.
So now, and what happens is a separation of charge, because what we have here is the protons can't move, they're stuck there.
Yeah.
But the electrons can. So let's use the left hand here. The field, fingers for the field is in, the velocity is to the right, so the force on an electron is going to be down. Every electron in the bar is going to feel the force down. So they're going to be taken away from this end, which will become positive.
Oh, so it creates a dipole.
Yeah, you get a dipole, exactly. It's just like...
Duh, that makes sense. Ha ha ha.
Okay, so that's called a separation of charge. It's an induced separation of charge. Okay, now here's the deal. The positive and the negative would want to hook back up. But as long as the wire is moving, the magnetic force would keep them separated.
Yeah.
So, yeah.
So as long as you're moving
you
through
stop,
there,
the force stops, everything goes back to being neutral. And you can
pressure.
probably see that there's also a connection between how fast it goes and how much force you're going to have because of this variable right here. And likewise, the quantity, the intensity of the electric field, magnetic field. And an electric field would exist between the separated charge trying to pull them back.
oh yeah, from the positive to the negative.
You got a bunch of positive here, got a bunch of negative here. The electric field is out of the positive into the negative. So there's an electric field that's acting on all those electrons trying to pull them back up. Out of the positive into the negative? Yeah.
Yeah.
Okay, so here's the deal. You've got a balance that goes on. You got the force that's keeping them apart, the electrons, and then you got the electric field that's trying to put them back together. So what this says is the force due to the magnetic field depends on how strong the magnetic field and how fast it's going. And the intensity of the electric field depends on how much charge is separated, right? But you notice that these go away.
They go away.
All right. This induced separation of charge produces a potential difference across the wire. Okay. You've got E inside here, and I should be using different colors.
Yeah.
And you've got the distance from here to here. So you have an induced separated charge. You got a potential difference across that short section of wire. And it's just like a capacitor.
Yeah.
Okay. So that voltage, that is emotional EMF. So before we talked about motional EMF, you know, about the whole thing moving. Now we're going inside the wire.
Oh, okay.
Before we were just looking at, you know, structures that were moving in the field. Now we're going inside the wire to take a look at what's really going on, what's making all this happen. So this electromotive force is also BVL. And that is the strength of the magnetic field, how fast the thing is moving, and how the length of the wire in the field.
And you got that from, where did we just get that from? BVD? You just showed me. Ed, that's right.
Yeah.
Okay.
Yeah.
Yes.
Okay. If the moving rod is part of a circuit, a current will flow. This is a classic physics illustration. You've got a horseshoe-shaped wire, and you have a rod that's on a frictionless surface. And the rod can be pushed one way or the other, and there's a magnetic field on it. Now, because the rod is free to move, it's also touching this, so you've got a closed circuit.
Yeah.
All right, so here the velocity is that way. What's this?
That's Lenz's law.
Yes, boom!
Yeah.
This is why I was pissed off when I found out that Stephanie was a senior.
Yeah.
We need more Moores in AP. So absolutely, so you have to do work pushing this across. Because there's a force, and how much work you do depends on how much force you have to exert as you go, and how much force depends on strength of the electric field and the velocity that you're going. Okay? So, Ohm's law for charge moving in B.
Voltage and resistance. Okay.
This is just I is V over R.
Interesting choice for E there.
Well, that's the one.
Yeah.
That's the electromotive
It doesn't look
force.
how your other E's looks.
Well, and it's different from this.
Oh, okay.
But it's voltage divided by resistance.
Yeah.
And that electromotive force is BVL. It's how fast you're moving that thing through how strong the electric field is, magnetic field is, I beg your pardon, and the length.
Current in the rod produces its own.
As you said, Lenz's law.
Yeah.
So the current in the rod produces its own field. And that interacts with the external field, and it resists the motion. That was that force we saw back in the other direction. So the force resisting the motion is the strength of the field times the current times the L. And what determines the current? Well, you know, I didn't write that down. I'm going to go ahead and back and write this down. And you got to remember to make small v, because that's not voltage, that's velocity.
Velocity.
Oops. We're almost done. So, if you're moving in this direction, the area is increasing. So you're getting more and more magnetic field on the inside. It's going to induce a current that's going to try to stop that. So it's
to decrease it.
It's going to decrease. So instead of the external field is this way, it wants to make a field this way.
Yeah. Okay, that makes sense.
So that's the direction of the current.
Oh, I see. Okay.
So how can you tell the direction of the current? Well, you're increasing the area.
Yep.
Lenz's law says it's going to produce a magnetic field. The current will produce a magnetic field to fight that. And so the current produces a magnetic field that's trying to cancel this out.
Yeah, because originally what we see, you know, our velocity is this way and our B field is in.
Yeah.
And all that jazz, but then we take a look and we say,
there's two
okay,
things going on.
the B field.
That's what pushes.
this B.
That's what. Let's use electrons.
Okay.
Well, now that's what pushes the current.
Yeah.
You've got this, it pushes the current in that direction. All right, that's one thing. But what's going on inside? That current makes its own magnetic field. So there's two things going on. There's that which makes the electrons, which makes the current move, the electromotive force. And then once you've got that current flowing, what direction will it be? It's going to try to cancel out
That one right
change
there.
in it.
Yeah.
Question: if I move it this way, if the velocity is in the other direction, what direction will the current be?
So
It'll be getting less and less in this direction.
Yeah. So my instinct to say is to decrease, but I want to think through it. So if it's if the area is decreasing
so
here,
the flux is decreasing.
that means the flux is decreasing, which means that Lenz's law tells you that the current it won't want to increase it.
Yes.
So
So that means it's going to try to make it in the same direction on the inside.
Same direction.
Which means the current's going to be in the opposite direction.
That's the part that I'm like, okay, if it wants to increase it, then we need to increase the B field in the inside, so it's going to add more to the inside. So it'll go, and the current will go the opposite direction. I mean, instantly you just say, okay, well the current will go the opposite direction because it's flip flop, but you want to understand why. Now, can you go back over here? I think I just need, my brain is a little mushy. Show me the algebra to get to the BVL again. I can't remember how you got there. Oops. Dang.
Okay. Yes.
Yeah.
Okay.
Was that velocity?
Velocity is
a
meters
distance
per second.
Yeah.
Distance over time.
Yeah.
Oh, I'm sorry.
Yeah.
Velocity is distance over time.
Be over.
Well, you can make it this way. You can make L over T is equal to velocity over times the width, right?
Oh, okay, yeah.
And so you got velocity times the width. That's the velocity time, and the velocity is how fast this is going. So that's this. Here's the length, and here's the width. So that width is this. The area is length times width, and the velocity is length over time, distance over time.
Yeah.
So this V
L, yeah, if you will.
L, and that's velocity L, is this guy right here.
Gotcha. Okay.
So what we've got is and velocity over time takes care of the time. And the area is velocity times the length, and velocity is width over time. So that's where this goes away, and that's where we do this.
Okay.
And I don't know if I explained that very well.
I'm just wondering where you got it from, because I was like, because we have so many different things up there, and I was like,
and the thing is,
I was like, where did it come from?
That's a wonderful question.
Okay.
All right, so watch this.
Okay. Ooh. Okay. So here, let me come around over there.
Well, we can put it right here.
All right. Okay. So it says a metal rod of mass 0.22 kilograms lies across two parallel conducting rails, and this is a little U-shaped thing, I think, that are a distance of 0.52 meters on a tabletop. It had a mass of 0.22 kilograms.
Yeah.
Okay, a 3 ohm resistor is connected across the left ends of the rail. Okay, the rod and rails have negligible resistance but significant friction with a coefficient of kinetic friction of 0.2. There is a magnetic field of 0.8 teslas perpendicular to the plane of the tabletop. So it comes out. Okay. A string pulls the metal rod to the right with a constant speed of 1.8 meters per second. Okay. To the right.
Oh, to the right.
Yeah. Let me double check. Yeah.
Yes,
string,
it is.
Yeah.
And what is it? 2.8, 1.8?
1.8.
Okay.
All right. The first task. Calculate the magnitude of the current induced in the loop formed by the rod, the rails, and the resistor.
Okay.
Calculate the magnitude of the current.
That's Ohm's law.
Yep. Induced in the loop. Okay.
And here, this is the electromotive force over the resistance. The resistance is going to be 3. We'll assume that everything else is no resistance.
So we need to
And the
calculate
electromotive force is BVL.
BVL. Yep.
That's BVL.
BVL over the resistance, and we have that 0.8, and we have the velocity is 1.8, and we have the length, which is 0.52. We know we divide it by the resistance.
Uh, 0.8 times 1.8 times 0.52 divided by 3.25. I'm going to call that 0.25 amperes.
Sweet. Okay. All right. Now it says calculate the magnitude of the force required to pull the rod to the right with constant speed. So we know the force is going to equal to Bill or BQV. Let's see what we got here. So we got the current, we got the length. Do we have the length for?
You know what? I agree that BQV should use, length is 0.52.
I was thinking about what length do you?
That's the length of wire in the magnetic field.
Okay, yeah.
Okay,
That's
but we might have made a mistake here, so I don't want to use this. BQV.
I don't think we can use Q because we don't have the charge.
We're gonna have to use BIL.
Yeah, they're counting on us not
So
messing
they
up.
want to know the force.
Yeah, calculate the magnitude of the force required to pull the rod to the right with a constant speed.
0.25 amperes.
Length 0.52 meters.
Oh shit. 0.8 times 0.25 is 0.52. That's 0.1. 0.1. It's 0.104, but
104 newtons. Okay. And then calculate the energy dissipated in the resistor in 2 seconds. That sounds like power.
It does.
Intravenous. Oh wait, what does it say? Oh yeah, so we can use our current, and for V we can use the electromotive force, right?
Yeah. The potential difference across here is going to be the same as the potential difference across here. Or we could use I squared R. Should give us the same answer.
We can try them both.
So we got 0.25 amperes times. Do you ever find the electromotive force?
I don't think
BVL.
we did actually, so we can calculate that.
Well,
or we
in
could
which
just use the
case,
resistance.
The hell with that. I'm
Yeah.
gonna do squared times 3, 1/4 times 1/4, 4 times 4 is 16. 1/16 times, I'm not doing this in my head, 0.25 squared times 3.
And then
0.18.
I think we multiply that by 2 seconds.
That's 0.8 watts. Oh, they don't want the power, they want the energy?
Calculate the energy dissipated in the resistor in 2 seconds.
0.8 watts times 2 seconds is 1.6 joules.
Wait, I think it's 0.118. Look at your calculator. I was like, wait.
How long have we been doing this?
I know, too long.
0.18 times 2 is 18 times 2 is 36. So that's 3.6. Waken, don't do this in your head.
I think it's 32.
Is it 2 seconds?
No. You're right. You got it. I'm not good with my eighths. Okay. All right. And then.
I still don't know what 7 times 8 is.
Calculate the work done by the string pulling the rod in 2 seconds. So work is force times displacement.
In the direction of the force, we've got the force that's 0.1 newtons. The distance is...
We don't have that distance.
Well...
Oh, there we go. In 2 seconds. Okay, so we just multiply it times 2. 1.8 times 2,
So the
right?
force is 0.1 newtons. That's what we got up here. Times 1.8 meters per second times 2 seconds. 0.1 times 1.8 times 0.2. 0.036 joules.
Sweet.
Is that it?
Last one. Compare your answers to parts C and D. So C was calculate the energy dissipated, 3.6. And then D was calculate the work done. Wait, where is that?
0.036.
0.036.
Here's work. Here's work.
Okay.
And there's energy.
Okay, now it says provide physical explanation for why they are equal or unequal.
Well,
Does that have to do with Lenz's law?
it has to do with friction.
Oh, friction, that's right.
Because there's you're doing work pulling on it, but you've got this much force it was 0.1 newtons, right?
Yeah.
And that was the force of resistance.
That was the force. That was letter B, I think. What does it say?
Oh, calculate the magnitude of the force required.
To
So
pull.
we calculated that.
Right there.
Right. So there's the force, but we have force of friction is going to be 0.2 times 0.22 kilograms times 10 meters per second squared.
Yeah. Mu times the normal force.
.44.
There it is.
So we've got...
So 0.44. Force of friction that way.
So friction is also doing work. And so...
What are our units? Mu doesn't have any units. It's just newtons. What do they say? I want to know what their answer is.
Oh, the energy dissipated in the resistor. Okay, so the energy dissipated in the resistor is a bunch. That was 3.6, is that right?
Yeah, I believe so.
We got 0.25 amperes. And get the cheat sheet out. We got 0.25 for that. We got the force. Oh, see the force. We're supposed to do both the tension and the force of friction.
Oh, it's got to be a total force.
So we did the
0.1. We have to also add in that. So we have to subtract it from 4.
So here's the force. That's 10. And so then we have to find the force of friction,
Which we did.
and which we just now did.
Yeah, which is 4.4.
So you got 4.4 plus.
Well, you subtract them, right?
No, because this is the electromotive force that's fighting it.
Oh, yep.
That's the. Wait a minute.
If you pull the rod with 0.1 newtons this way, does that mean the electromotive force is also fighting it with 0.1 newtons?
So what they're asking is calculate the magnitude of the force required to pull the rod to the right at a constant speed. So we calculated the force required to pull this, to develop that current. All right, so that's the force that's making the current that you have to overcome. There's also the force of friction. So the total force is the force required to just pull it past there, because the back EMF that's fighting you, plus that. So it should be 53 newtons total. 0.1 plus. Yeah, and they used, we got 43.
So it must be 0.43. Oh yeah, we got 0.44.
All right, it doesn't matter. So, but this is 0.1. Oh yeah, 0.1. So 0.54. You know, rounding. I don't give a shit.
Oh, I see.
So that's correct. And then so now we've got the total force.
0.54.
Force total.
And now we put that down there.
0.54, which is going to be 1.8 or 0.18?
1.8. Is that right? Wait.
0.54 times 1.8,
Yeah.
0.972. So it should be 0.972 joules. Okay, calculate the energy dissipated in the resistor. C. Energy is PT. Yeah, and they use I squared R. You got 0.38 joules. We got the decimal in the wrong place.
Oh, you're right. Sorry, yeah. That's because we did it in our head.
So it's 0.36. Now it's making more sense. And see, that when you take an AP test, see how they are? They ask this question at the end, it'll say, did you fuck up somewhere?
Yeah. So we get 0.36 joules there, and how much work it takes us to do is 0.97 joules. And so, that's how much energy, I'm sorry, that's how much energy dissipates in the resistor.
Okay, and then this last question, how come the energy is less, how come the work is less than the energy you get out of it? That's because friction.
Okay.
Friction is doing negative work. And that's it.
Sweet. Oh.